Thessaly. After working for some years in the industry as an automation engineer, he joined the University of Hohenheim in Germany, where he obtained his PhD in 2016 and habilitation in 2022 in agricultural engineering. Since October 2021, he is serving as a full professor of agricultural engineering in Geisenheim University in Germany. He's also serving as an associate editor of computers and electronics in agriculture and is a member of the editorial board of Smart Agricultural Technology, both published by Elsevier. He has participated in more than 20 European and national research projects. In the past, he has coordinated the ICT Agri projects, Paraforos, while currently he is a WP leader in the Horizon 2020 project, Robo for Crops. He is the author or co-author of more than 50 papers indexed by Scopus and published in journals or presented at national and international conferences. His research interests include agricultural machinery automation, isobus technologies, unmanned ground and aerial vehicles, and decentralized and resilient digital farming systems. The presentation is going to be precision agriculture in the digital era, Dystopia or Utopia. And I will give the floor to you now, Dimitrios. For everyone else, please make sure that your mics are muted during the presentation. Otherwise, I'll mute them. And we have around 45 minutes, and the last 10 to 15 minutes, we will spend them on discussion and questions from the audience. So the floor is yours.
Thank you very much, Ahmed. It's really a great honor to accept this invitation from Dalhousie University in this series of speakers. Thank you very much for the introduction. Just quick feedback, if you can see my presentation, if everything is fine, and then I can proceed. Okay, very nice. So the title, Precision Agriculture in the Digital Era, Dystopia or Utopia. This is something that has come to my mind the last months, to be honest, after a very nice publication from one of our colleagues at the University of Hohenheim. And what is bothering me, also talking with colleagues in ecology, where are we going to? Where are we reaching? What are we trying to reach with this digital era that is really coming the last years in precision agriculture? What is the path that we need to follow? Just to mention that at the moment I'm affiliated with two universities, my previous university, University of Hohenheim, and also Geisenheim University. Just Ahmed mentioned many things about my past. These are the main stations in my background until today. So I will not go through it again, just to get an impression where I come from, Europe. This is Greece. I come, as Ahmed mentioned, from the northern part of Greece, where I grew up on a farm. My father was a farmer, so I was always trying to go back to farming, even though that I studied automation engineering. This is my home area, close to the Mount Olympus, in the northern part of Greece. And this is the area that somewhere around April, I would say, when the peach trees that we're also cultivating, and I'm still owning 1 hectare of peach trees, very happy about it. This is the blossoming time where the valley is turning to pink from the blossoms. With the monoculture, I would agree that sometimes, although it looks nice, the biodiversity issue comes into play, and I would be happy maybe to discuss about this. So after starting from my reference point, since I'm an engineer, I like to talk in engineering terms, the point 0.0. I moved to Germany. Since 10 years, I'm initially at the University of Hohenheim and very close to the Geisenheim University, where I share my time between these two universities. This is the palace of the University of Hohenheim, close to Stuttgart. It was established 200 years ago, and this is my new place, the Rhine Valley, the Rhine River, and here it's you can see the vineyards, I'm trying to balance between arable crops and viticulture and horticultural crops. It's not always easy to transfer the technology, but it's an interesting mixture at the moment. So coming back to the title, Dystopia or Utopia, this is the illustration that is on the paper from my colleague and how the future could look like, or if we can be somewhere in between where we should try to be, and how precision agriculture can help us. Because there are a lot of voices that are afraid that farming is getting industrialized. So with the way that we are taking, that we are moving closer to the right side of the slide, where we are reaching more to the dystopian scenario. The dystopia in it is the scenario that everything goes wrong, that our entire farming processes has been industrialized, humans are not happy, the plants are not happy, the soil is not happy, the environment is not happy. And on the other side, we have the utopian scenario. In the utopian scenario, everyone is happy. We are still using robots. We are still using automated machines, precision agriculture, digital farming, you name it as you like. But then we are coexisting in harmony with the environment. We are respecting the soil and the environment, and we have reached sustainability, at least, in our farming processes. So where are we going to? And this is what I'm trying also somehow to show in this presentation. Of course, I will go more into the technical aspects as well. But let's make a step 100 years ago, 1928. At that time, we have the patent from Harry Ferguson about the three-point linkage. This really revolutionized the interface between the tractor and the implement. So how mechanically we could connect any implement that the growers, the farmers were having to every tractor. At the same time, in Europe, the first pneumatic tire from Continental was introduced. And this really revolutionized the interface between the tractor and the soil. It really increased the traction. Until that moment, we had only these steel wheels that they were not optimal. So we have in 1928 these major milestones in agriculture. And at the same time, the New York Times were having some second thoughts about the march of the machines that make idle hands. And we can see that it was maybe a dystopia in the horizon, that they were, at that time, we had the Industrial Revolution at its full power, so people were worrying that the machines will not be offering any more jobs to people and we will have many problems. We are somehow to a similar case in terms of automation and artificial intelligence. A lot of people worry that robots, machines, automation, intelligence will bring agriculture in a little bit wrong direction. Let's go 60 years later. And now really go to precision farming, because the title is about precision farming and how precision farming is today. But precision farming is not something new. Precision farming has started more than 30 years ago. Here you see the work from Professor Auenhammer at the Technical University of Munich. At that time, it was together with company Amazzone, who is very known for fertilizer, centrifugal disc spreaders, and many other implements. So at that time, there were efforts. Here you see on the right side, there was somehow, let's call it a PC or a terminal on inside the tractor. They had this hardware chip card that they were making recordings. So they had sensors that they were providing information how to apply fertilizer and chemical products in a variable manner, and this information was recorded somehow to this card. So here, in this example, this person was going later to his office in the evening, was taking this card that had recorded the information. There was a dedicated hardware that you had to insert this card, and then you had in your PC at least the initial farm management information system, an initial FMIS, let's call it, where you could transfer and you could record the information at what was happening in the field. So as I said, precision farming is not something new. But let's check what is new in the digital era, as we are calling it. At that time, the best case, farmers had a PC or some kind of hardware. And this is what they are having today. This is what is available. All kinds of sensors are everywhere on our mobile phones, in the sky in terms of satellites, drones, sensors on implements, sensors on tractors. But except that, we have all kinds of interfacing devices like tablets, smartphones, terminal PCs, and so on. And what is also at the digital era, as we are calling it, is the cloud-based services. From big data, from digital twins, all kinds of web cloud-based applications. If we check the farmers, what is happening on the farms today, you will see all kinds of electronics. Isobus has really revolutionized the farming and agriculture industry, also forestry in many cases. All kinds of sensors, applicators, in terms of fertilizer spreaders, in terms of sowing machines, in terms of crop protection, but also interfaces, farm management information system, analytics, and so on. So this is what we have at the moment at the physical level. On the farm, all these machines and sensors are working all day. But as I said, because I grew up as a farmer, and if we talk to farmers about the digital revolution, and we start discussing about machine learning, artificial intelligence, Internet of Things, for them, it's difficult to understand what is the benefit. So why should we care about this digital era? What will be the benefit for us? Because at the end of the day, we have to go on our tractor, take the fertilizer spreader, and apply fertilizer. So this is really something that we need to explain to them. That's why we are trying to give a framework, to make an architecture. So in terms of digital technologies, we can say that in the core is what I have shown, the Internet of Things, wireless sensor networks, edge computing. This is devices that with increased, enhanced intelligence at the field level, the isobus, unmanned aerial vehicles, unmanned ground vehicles, and so on. If we go one level higher, we have the cloud computing. So we have infrastructure as a service, platform as a service, software as a service. We have all kinds of cloud-based systems. What is happening at the moment is that we are going even higher. We go to big data analytics, artificial intelligence. Deep learning is a term that you can hear everywhere in the conferences that I have been visiting. 50% of the publications are related to artificial intelligence, so there is something there, definitely. And then we can talk about digital agriculture. In order to, from my perspective, to be able to talk about digital farming or digital agriculture, we need to have all these layers. So to have the analytics, to have the cloud-based infrastructure to reach to the physical level. I don't think that we can do big data analytics or artificial intelligence on a desktop PC anymore. I recall my days in the late 90s when I was doing some neural networks in MATLAB, but these days are over. Everything is really on the cloud now. The services is there and the computational power is there. So we have the physical layer, and now we are talking about the cyber layer. What is missing and what we also need to find is the interoperability. There are still issues. How do we bring these two worlds together? And this is how we also, the farmers are asking, how will be my connection with the cloud? So we have a cyber digital world, a cloud level with all kinds of information, sensing from satellites, as I showed, from drones, and this multi-layer information. And from another side, we also have the revolution of digital twins. We can really have a representation, a digital representation of three levels, usually I'm calling them. The machine level, the operation level, the task, if it is fertilizer, if it is sowing, and so on, but also the farm level. So we are reaching a point that we can really reconstruct in our PC or a cloud-based system a digital twin of these three individual levels. So let's check a little bit how are the interconnections into this digital farming system. This will also help you understand the frame of our work here in Geisenheim and Hohenheim University. So the bottom layer, we have the IoT, we have the Internet of Things. We have the crops that we are sensing the crops with all kinds of sensors. It can be soil sensors, soil humidity, microclimate sensor, and nutrient sensor, and so on, because we need this information. We have remote sensing, if it is drones, if it is satellites, but at this level, we have also the machines and the robots that are taking some action, that they are doing something, that the machines will go for sowing, the implements, or even nowadays, we even have robots, and it's very common, specifically in specialty crops that they have moved recently in viticulture. The robots, the use of robots is increasing rapidly. So what we need here in this digital farming ecosystem is the cloud computing. We have data lakes where we are storing the data. And also here we have the farm management information system. This is the presentation layer, and many tasks, many strategies are coming from here and informing the machinery about the strategies. And it can be an application map, for example, about site-specific fertilization. So then we go one layer up and we have the big data and artificial intelligence. All kinds of agronomical algorithms. It can be also black box algorithms that are only fed by data. That's why we are moving also a lot, and I know many companies that they have nothing to do with agriculture. They are data processors, but they are really interested the last 5 to 6 years, this is what I'm seeing, to obtain data from agricultural processes and even create new data products. An example is insurances, to provide targeted insurance packages to farmers, or insurances for robotics. When someone buys a robot, he or she needs also some kind of an insurance contract. But we also have reports and open data that the companies are helping, that's why I'm calling it big data services, are helping the growers, the farmers, about their reporting, about their cross-compliance, how many fertilizers they are applying, how many chemical products they are applying, because this is needed also to inform the public authorities that they have the task to impose new regulation. And here we have agronomic advisors that they can benefit of these data products and give more sophisticated advices to farmers. But here I have to say, although the farmer is really up left at the corner, the farmer is at the center. He's at the center of this entire process. This is, we should not be forgetting that the farmer has to spray or cultivate, has to harvest, maybe sell products of data products. We can see that maybe in the future, but also sell his or her crops, inform the public authorities, and so on. And that the farmer should use the farm management information system to interact with the machines so the machines can do actions at the field level. So this is what we are trying to cover with our research and our activities in general. I have prepared some slides about some of our projects. I have here 5 projects. It will be just some very targeted information, just for you to get an impression of what we are doing. We are working very closely with companies here, with companies in Germany like these machine operation profiles generated from isobus communication data was a project together with Class company. The idea was they are selling worldwide their machinery, but what they are lacking is how are these machines being used at different locations? How we can really make a profile of a use of a machine, because then what they can do in the designing of new products is that really to design and develop products that are very much targeted for specific countries. I will tell some more details in the next slides about that. The second one was the Paraforos that also Ahmed mentioned, the ICT Agri project that I was coordinating and finished just 3 months ago. And here is to create a digital farming system for site-specific nitrogen fertilization in winter wheat. And here we want to use really standardized tools one of them is isobus, this electronic communication standard that is really worldwide in agricultural engineering. How can we connect all these components? How can we establish this digital farming ecosystem to go from sensing, analytics, decision making, and then action in a standardized way? These are really two projects from the past. Currently, we are working on the Ropes for Crops, a European project that tries to revolutionize the way that robotics are working on farming. And here, one of our tasks is to bring isobus on agricultural robotics. And that will help us to connect the robotics that are working on the farm with existing isobus compliant machinery that the farmers already have on their machinery fleet. We see the one path of the robotics in the future, not really as an island, as a proprietary solution, but robotics could be integrated into this ecosystem that I just described. The other one is the MR digital, and here an important topic that has to do a little bit with a dystopian scenario and how to avoid this scenario is how can we create decentralized and resilient digital farming systems, and mainly because we are bringing everything to the cloud. What happens if there is no cloud anymore? We'll give some answers in the next slide. And here is about a farming simulator. I don't know if you are aware of this known game from Giants. This is for many years on the market. That is really simulating an entire farm with tractors, implements, all kinds of machinery. We had a project the last years that John Deere initiated. How can we bring precision farming into this game? That was nothing about it. And we want to do that because the last years we have noticed that we are developing many technologies, but these technologies never reach the growers, or they reach only to a limited extent. What we want to achieve here is to increase, first of all, awareness of what precision farming can do. So also the general public is not afraid of digital technologies, of precision farming technologies, but we show that it's helping in sustainability, and at the same time to help young farmers, the farmers themselves, by growing up with these games to see, okay, I can use a sensor for applying fertilizer. I have seen how it's done at least. Let's go through this project. So the first one, we use this class liner 4000, a 4-rotor rake. And this machine is sold, as I said, worldwide. And they wanted to see, for example, how is it used in New Zealand, how is it used in Germany, how is it used in Brazil, in all over the world. And we created a methodology because the information that is flowing on the isobus. So there is a cable connecting the machine and the tractor and the operator presses button. So when this is normal working mode, when the operator is on the street, presses the button, the machine is folded, and it is on transportation. But this is recorded. We can use this information. When the rotors are lifted, that means that the farmer is really at the headlands and is making a U-turn. So that we know that at that time the machine is not working, it's turning. So we obtained from 3 different machines. We did it within Germany, in different locations of Germany, and we developed a methodology. We had a normal canvas data logger and some GNSS to have the location. Based on the machine operation time, we divided in main time, working time, and turning time, in fault time, like non-productive time, preparation, row time, and so on. So my colleague, Dietrich Kottenbrock, as he was working on his PhD, developed a MATLAB software that you could bring all this data that have been collected within 1 year from each machine, and it was making an analysis at the end based on this isobus information. You could extract the work time, turning time, fill time, the categories that I have just shown. And here is just an example of 4 fields that we use the machine. You can see here with different colors, the preparation time, with yellow, the row time, with green, work time, turning time, with cyan, and so on. What is interesting from this project is that our colleague created a spin-off company 3 years ago. The company is called Exatrek, and it's very much successful at the moment. he developed his own hardware, a piece of hardware. He transferred the methodology that I just showed you in MATLAB. He enhanced it into built-in software connected to a mobile phone. This device is connected to the isobus of the tractor, and in real time is informing the operator about the efficiency, about the fuel consumption, if it is normal, if it is maybe more than appropriate or more than is used to consuming, how much time does he or she is spending on the headlands, and so on. And please excuse some Germans here, but you can get the point. This is the hardware, you connect it, the isobus, and you're really connected and receiving isobus information and analytics in real time. Now it's also connected to the cloud, to many solutions. At the moment, this device is installed in more than, I would say now, around 2,000 tractors and machines all over Germany, and this is expanding. That really showed a need and also the potential for digital farming and digitalization. Let's move to the site-specific fertilization. This was this ecosystem, this digital ecosystem, and how can we collect information from different sources, remote sensing, soil data, and so on. We name it as a API, as a middleware that is receiving all kind of information. We have the analytics, we have the decision support, and then based on the decisions, we use the tractor electronics to implement the strategy. This is very common to have a fertilizer spreader for a centrifugal disc spreader, an isobus terminal, and here you see an application map. So we have developed an application map based on the sensing that we had. We tested what was the issue here. How can machines that we are having available today, how can they cope with these application maps? So even if we could have an application map that has a high spatial resolution, can the machine really cope with this? A fertilizer spreader that has 24 meters working with. This is the application map that we had, and this is the as applied information, what the spreader actually did. And we wanted to know exactly where the fertilizer landed. So we used different kind of sensors. Here you see a total station following a prism, an IMU. We used the isobus data for the rates that the spreader was applying. We had the geopositioning, the georeference, another photo of the total station. We modeled the entire process of the spreader. We modeled the ballistics and its granule flight trajectory. And at the end, we had the spread pattern. So where the fertilizer is landed every time. And here, because we are talking about a two-disc spreader, you see the blue one, the left disc, the red one, the right disc, and the joint one. We had a 3D a fertilizer distribution based on our modeling. We did also validation, so it's very common in validating static spread patterns. We placed these boxes. We drove with the spreader to have a full path, also to have this spread pattern. And then here we really validated the measured one. So you see with the X, the red X, the boxes, the mass that we have measured. We have a fitted distribution, and with the green line, you see the modeled one. So our model was somehow accurate with a RMS value equal to 2%. So it was a decent match. So what we did then, we checked prescription rate. Here on the bottom, on the upper left corner, you see what was prescribed, so what we wanted to apply. On the left up, we have what was applied based on our model, based on the validation that we did. And here in the bottom part, we have the difference between these two maps. So how good the spreader performed. This has nothing to do that much with the spreader performance. This has to do a lot with the resolution that we are having, and the change, we noticed that many problems had between two zones. So when you were changing from one management zone to another one, what we try to do together with the companies is before you go to apply your fertilizer prescription map, to do a simulation on your FMIS. And then your FMIS will tell you, to your agronomic advisor, look, the map that you have given me is having some challenges. Maybe I will not be able to apply to the extent that you would like to. Let's move on to the current project that we are having, the Ropes for Crops project. We are 16 partners all over Europe. What University of Hohenheim is here is work package 2 related to the smart implements. As I said, we want to connect the implements with, we put sensors for detecting, we put enhanced capabilities on these implements to autonomous vehicles, to robots. Here, what is important is to consider both aspects. So also the technical with sensors and digital twins, isobus, whatever I have mentioned, but we should never be forgetting that there is also the non-technical aspect that comes into play. And the farmers have to cope also with non-technical aspects. And this is one main of the aim of the project, is to bring our robotic solutions to farmer associations in 4 countries in Europe. We have them as partners, and to really use the solutions, these digital farming solutions. And we are co-creating with them the way that we will be using these solutions. Here, we also have the term digital twin or the cloud-based system. We call it farming controller, and we have 2 robots. On the left side, you see the Roboti from AgroIntelli. On the right side, you see the SEOL from Agriculture. The Roboti on the left side is mainly for arable crops and vegetables. We will be using it in the Netherlands. You see this type of robots is like a tool carrier. It's not really the small swarm robots that are many working on the field. That's why here we want really to use industrial commercial machines. You see here a precision sowing machine, and being used with this autonomous vehicle. Also on the right side, the SEOL robot from Agriculture from France, we are using it for vineyards, for weeding vineyards, and we are also enhancing the capabilities of the weeding machine with cameras and context awareness. And the weeding machine is communicating with the robot by using isobus. The idea behind it is what I mentioned. You have an isobus compliant robot that can be connected to potentially to all isobus compliant implements. So we move on to the MR Digital and to resilience and decentralized system. So, as I said, we are moving everything to the cloud. If everything is successful, in some years, this cloud cyber-physical connection will be working. We will be having all kinds of information on the cloud. Routes that our autonomous vehicles need to follow. All kinds of information, logistics. Then we will be relying a lot on this connectivity. And then comes the question, what comes if there is no cloud anymore? Some weeks ago, we didn't have social media for 6 hours, if you remember. And it was a very big issue for the entire world that they could not really communicate. Think the farmers, if they are really basing their entire processing and production processes on the cyber-physical connection. So what should primary production stop? In any case, no. Primary production should continue. And we have divided in many cases, many scenarios here. What do we mean that there is no connection to the cloud? Does it mean 1 hour? Does it mean 1 day? Does it mean 1 week? Or does it mean that 1 month and I don't know when this connection will be reestablished again? So what is really important to remember and what we are trying to do is to create this decentralized system. So here you see a GeoBox, as we are calling it. It has different names. It is like a backup solution that even when there is no connection to the cloud, at least there is a digital farming system that is running locally And at least the machines will not be sitting there waiting for the route to follow or the application map, but they can really go and proceed with production. This was just the publication some days ago, and if you really want to see more information about the conceptual framework of a decentral and digital farming system, please follow the link here on this slide. So I'm reaching to the end of my presentation, and this is, as I said, to increase awareness. There is a new release soon from the Farming Simulator in some weeks, the Farming Simulator 22, and this is the mode that we have been developing for this game that is using sensors, that is using different kind of technologies related to precision farming, and we are integrating it into the game. Just to ask, is it, I don't know if the sound is there, most probably not.
No, I don't hear the sound from the computer.
Okay, but just some slides, just to see, this is a...
But we see the animation anyway.
Okay, but you can hear me, yeah?
Yeah.
So this is by John Deere initiated. This you see the partners with University of Reading and also Group OEN, and also the Polish Academy of Sciences, funded by EIT Food. Also the ski and spray technology that you detect the weeds and then you proceed. Variable rate seeding, variable rate weed control, variable rate organic, soil maps per phase, and so on. So you see that we are trying to approach people, young people that are playing the games, or it doesn't matter, but the older people, but to increase awareness of what precision agriculture can do. Because people might have a different view, and if the pressure comes from the consumers, for example, that there are the technologies that can help us, then the policymakers can also provide support to farmers to adopt these technologies, because they need support in adopting new technologies. So to conclude, I would like just to have some suggestions here, because as I said, I never forget my farming background, and we need to think like a farmer in our ways of bringing this digital revolution to the farm. So it doesn't make sense to shout at the crops if something does not work. We should not blame the crop for not growing fast enough. We should properly irrigate and fertilize. We should protect our crop by providing all kinds of means that we can. And we need to remember that we will have good seasons and we will have bad seasons. It's not every year that we'll be having good seasons. So it's for centuries like that. Soil and crops do not care about data. They don't mind at all what is happening. They don't care about the connection to the cloud, if the connection is there. If not, they don't care about artificial intelligence. And what we need to do to reach to the, closer at least to the utopian scenario, is to apply expertise to support this ecosystem here. At the end of the day, it's the farmers, they are the ones who need to go and take some actions, and they will face the consequences of these actions. The aim should be always to support them and not replace them. We don't want a farming-less or farmer-less farming. We want them there to be able to take decisions, and we really need to support them in this decision-making. So I see our mission is to really to get as close as possible to utopia and try to avoid as much as possible the dystopian scenario. Yeah, with this, I would really like to thank you, and I'm looking forward to our discussion. Thank you very much.
Thank you very much. A great speech, very much aligns with me personally. So I'm happy that somebody else is speaking the language of Isobus as well, because as you said, I think an important point you mentioned is that the very little people understand these things, and this is always difficult when we try to get funds or to try to expand the implementation of technology, is to bring it to a level that general people understand what we try to do. I'm sure there are questions from the audience, so I'll see if anybody has a question first. So please raise hands if you have any question, and we will take them in order. Okay, we start with Muzammil then.
Hello, sir. So my question is, in a practical application, what the challenges you faced till now working with the ISO bus? Yeah, can you name some of them, and then we can have a discussion on that one? Yeah, thank you.
Yeah, definitely. There are many. I have to admit, there are many. There are not few. ISOBUS is an industry standard, but the standard is not always perfect. We know that. We have seen that. It's, they think that how many agricultural engineering companies exist, that they have come together to create a software protocol that really helps them in communicating. So we have faced many times that something that's supposed to work doesn't work that easily. But that's why we are working very closely with the Agricultural Electronics Foundation. There is a foundation, there is a union of people, industry people, academics, farmers, that we bring up all these things in order to improve newest versions of ISO. So one thing is the interoperability, that although it's an industry standard, I have to be honest, and that sometimes we have issues, but we always find solutions. I have to admit. The first one was that. The second one was the limited bandwidth. Think that ISOBUS is based on CAN bus with 250 kilobits per second. We are discussing about wireless communication in 5G now with gigabit per second, and ISOBUS is still 8 bytes of messages. It's from the 80s. It's based on CAN bus 2 from Bosch that was developed in 84, and we are still having this protocol. There are many ways with colleagues that we are working on the fast, high-speed ISOBUS. It's coming up, hopefully, soon. That will be in parallel together with the CAN bus. You will have the Ethernet. We cannot really get rid of. We don't want to get rid of. The CAN bus is offering a unique proprietary issue with components that guarantees the signal that you want to send will reach its destination no matter what. So when the engine is sending a signal to the PTO or vice versa or whatever, you can guarantee, you can be sure that your CAN bus will bring it with the highest priority to its destination. While with Ethernet, we know the problems. Think if there is some seconds of delay when you press the brake. Just of that only. With CAN bus, you don't have such issues. But of course, when we talk about analytics, this is something else. That's why we are developing in parallel this. So these two things mainly we have as ISOBUS. That from one side is sometimes the plug and play doesn't work immediately, and the bandwidth issue that we are really pushing the limits at the moment of ISOBUS.
Thank you, sir. That answered my question, sir. Thank you very much. Yeah.
Thank you.
Thank you, Dimitrios. Just one point, a comment from my side on this point. You talked about interoperability also, but I think, and maybe you touch on it in your answer now, there is a type of interoperability needed between the sensors and the ISOBUS before we go from the ISOBUS to the cloud and so on. And this is something that, in technical terms, need to be addressed all the time.
Definitely.
Yeah, let's take the second person, Imran.
Hello, Dimitrios. Thank you so much for such a nice presentation. I have two questions to ask. Like you talked about the application map, like it's just about the applying, or you showed the application maps, or you didn't talk about like the detection actually, how you detect to apply, like it's also related to that. And one thing, and the second is about the backup, decentralized. Like what hardware you use, like is it real time? You share the data like in real time to the cloud, or the backup you talked about in decentralized. So can you tell me in detail about those things? Yeah, thank you.
Yes, the first question about the sensing part of before we reach to the application map. Yeah. Well, I have to admit that since I'm an engineer, honestly, I'm trying the last 20 years to understand the plants, the crop plants in the soil, and I'm still struggling. It's really something extremely difficult. With engineering, you know if it is working or not working. In nature, it's never like that. It's always something in between. So, about the sensing. What we were trying to do in our Paraforos project. That's why we had also other partners that they were specialized in algorithms, in modeling, in crop physiology and biology, and so on. We were taking, for example, from satellite data, different kind of indices like NDVI, NDRE. There are so many, and it's still a question to me which one correlates the best with each crop plant at which period, and some are. The NDVI may be better in the early stage of wheat growth, but then it gets saturated fast, while NDRE can be working better. There are so many. So we had satellite and remote sensing data. We had map-based soil data like electrical conductivity that it was coming into play. We had weather data. So the prescription map was also defined how the weather will be within the next days. The strategy of the grower. What does the grower, the farmer want to do? Want to apply more where the crop plants are better because these crop plants have a higher potential, or he or she tries to balance the crop. Different agronomists have different approaches on that. So we try to build a system that can really offer a tool to farmers and advisors. So we really need, our aim was not really to make a prescription map that works perfect, because we don't know that very good. But we try to offer the tools. That's why it was the standardized tools in the software, in the project. A platform that can collect all this information, and then someone can develop the prescription map. Hopefully this answers the first question that you had. I just mentioned all various sensor data sources that we are using. Then going back to the next question about the backup system. There we use, the most important is, we have a farm server, as we are calling it. So think that this is a desktop PC on the farm office. But this desktop PC is really having the essential information that is needed for production to continue. This desktop PC cannot have all functionalities that the cloud-based system has, or at least the advanced analytics that we are having. So there is a desktop PC. Imagine that this is your farm, you have a PC, and it might be a Wi-Fi that is working with a generator. So you have a generator at your farm to have electricity mainly for your farm, and then you have no internet. Imagine you have nothing, but at least, that's why we're describing in the paper different scenarios of this. At least you have a local network that is working, and then at least the machines can communicate with this PC and exchange the information. Think in terms of the future digital system. At the moment, maybe this is not the case on the farm level, but this might be the case in 10 or 20 years, that the connection and this cyber-physical connection is really a reality. Then we need to have such a system ready. So it's not a specific hardware or software. It's an FMIS on a desktop PC that can run on this local network.
Okay. Thank you so much. Thank you so much.
Thank you.
Thank you, Dimitrios. I'd like to expand more on this topic, but we don't have much time, and we have one more question coming from Humphrey this time.
Thank you very much. Thank you very much for your presentation, Dimitrios. I would like to find out about the See and Spray for the weeds. I would like to find out what are the operation speeds for this See and Spray technology.
Well, yes, that's true. I have to admit that I don't have a direct answer to you. This is something new, and this is because we had John Deere in the project. This is also how they call it, their commercial name, and they want it. I don't want to say something wrong about this specific product, yes? But what we are doing in our work with other products, like the project that we have, the Horizon project that we have, we are not talking about normal speeds, how to call it, that the farmers are used to of 10 or 12 kilometers per hour. This is something that goes slower because it's the processing time that you need. So for example, in our project that we have a similar case, we have on the robot, we have a perception unit that with cameras that checks the canopy. And then we have a sprayer, an isobus sprayer that is receiving this information from the perception unit. And this is connected to a robot. So there we have seen that at the moment, the maximum speed that we can reach maybe 3, 4, 5 kilometers per hour. But this is, when you have a robot working there, it's not that crucial as if you have a farmer with a tractor working there. Because if the robot can work day and night, it can be that it can drive slower. So speed is an important aspect in terms of computational capacity, computational power that you have, and it's also the distance that you have. So where do you place your sensing unit? If it can be placed really at the front of the tractor, and where is the actuating point? So if it is the nozzles at the back, you can understand the more the distance increases, you have more time. When we had a small robot with a mounted sprayer, that it is in total 3 meters, the distance also decreases, so you have to drive slower.
Sure. Okay, thank you.
Yeah.
Okay, thank you, Dimitrios. I see, okay, there is one. I'll take final question from Ali.
Hi, Dimitrios. Thanks for your presentation. Thanks. Do we need any special standards for tractors also? Maybe in future we will have some tool carrier tractors, like just to carry the tool, like nothing behind of the tractor, just grab the tool from their center and carry it on the farm. Do you think we need a kind of standard for these kind of tractors, like a tool carrier?
If I got it correctly, Ali, you mean to have 2 vehicles on the farm, or to have 1 vehicle with 2 implements?
One source of power. We call it tractor, to take the seed drill, also take the sprayer, take the whatever it needs, and it's a kind of it has a standard attaching mechanism, and just it can carry it and make and provide the power to power it, and maybe connect it to internet or whatever data transfer. Do we need the standards for these kind of power source in the machine, in the field? So, we have a standard tractors and a standard three-point hitch. So do you think we need a standard hitching system for just carrying the machine? You show us some special robots carrying some implements. Maybe in future we need some standards for connecting different kind of implements to one power unit. I call it a tractor. Do you think we need such a standard or not?
Well, from one side, what we are using here is to use the available standards when this is possible, because it's not always possible. And so what the aim is in these tool carriers is to have the isobus for electronic communication as a standard communication as a standard for communication, and then to use a real 3-point hitch. So to have a 3-point hitch to mount the implements. What we need, because isobus is from one side only a communication protocol, a standard. It's for the interaction. What we are trying to do now is really to enhance isobus to include more process-related variables. And there we have issues. So I will take it a little bit to the abstract level and we come back to this. So, for example, we are discussing with colleagues about ontologies. When we are talking about ontologies and process-related information, then we are reaching the limitation of the isobus. The isobus was not built for that. The isobus was built to tell what is happening between a real tractor and an implement in terms of hydraulics, in terms of whatever. So from one side, we have the ontologies in order to standardize the entire processing in terms of processes and operations. And then the more we enhance our machinery with robots, with other types of implements, implements connected to the farm PC, connected to the cloud. Isobus has also some working teams. An example is the team about in-field communication, wireless in-field communication. So in the future, maybe the vehicle at the front and the implement at the back, they are communicating wirelessly. When hopefully the wireless communication is that much established and reliable, maybe there is no need anymore for a cable between these two. So you see that we are enhancing standards in this direction, because it's clear that proprietary solutions in farming, in arable farming especially, they haven't really established themselves. So we see that the solution should be somehow standardized or being part of a standard that is existing already.
Okay, thank you, Dimitrios. I'm sure there are more points to discuss, but we are unfortunately over time already. So we will leave it here, and I'm sure that people who have questions can reach out to you directly.
Feel free, it will be my pleasure.
Yeah. And me and you will be discussing soon as well.
Definitely, it will be my pleasure. Thank you, all of you, for joining the lecture. It was great meeting you. You are really warmly invited to join us, to visit us whenever you can do that. It will be a pleasure, and we will catch up with you definitely, Ahmed, on possibilities to enhance our collaboration.
For sure.
It was really nice talking to all of you. Thank you very much for inviting.
Thank you, and thank you for the audience for attending today and for organizing.
Thank you so much. Thank you so much. Appreciate it. Thank you.
Thank you very much. Bye-bye.
Goodbye.